last lecture, we looked at the interactions of the radiation field with atoms. In particular, we looked at the Rabi model. It is a semi-classical model in the sense that basically you have a two-level atom. This is the ground state and that is the excited state, and the interaction between this atom and the radiation field is through the dipole operator D. This is a single mode electromagnetic field in free space. This is the radiation field, and we took this form for the field so that it was time dependent but varied sinusoidally. And then we saw that the population moved from the lower level to the upper level and back again in a sinusoidal fashion. There was a natural frequency in the problem, the Rabi frequency, and there was a certain instant of time when, even if the atom initially started in the ground state, at that time it would have moved completely to the excited state, and therefore there was a population transfer to the excited state. Now, this is a semi-classical model in the sense that the atom operator, this is an operator, and really we were interested in matrix elements of this form. This part of it was quantum, and this electric field was merely E naught cos omega t. Then I moved on to another model, and that was for radiation field inside a cavity. It is a fully quantum mechanical model. So, the field is treated quantum mechanically in the sense that the electric field is written in terms of the photon destruction and the photon creation operators. And essentially, in a situation like that, this was the first model. The second one had, apart from, this is the polarization vector, apart from constants that was a function of epsilon naught and the volume and sine kz, the electric field had a dependence on the photon creation and destruction operators in this manner as A plus A dagger. A is the destruction operator and A dagger is the creation operator. And then in that situation, we could write down the Hamiltonian for the atom field interaction. The Hamiltonian itself was the Jaynes-Cummings Hamiltonian. This had three parts. We had discussed this Hamiltonian and written out H atom as H cross omega naught by 2 sigma 3, where this operator is simply E minus Gg, and H cross omega naught is this difference in energy. And then we had H field, which was H cross omega A dagger A. And then there was an interaction part, which was H cross lambda sigma plus A plus sigma minus A dagger. Sigma plus takes the state ket G to ket E, sigma minus lowers ket E to ket G. Of course, sigma plus acting on ket E is 0 and sigma minus acting on ket G is 0. And you can see that this process would take the ground state of the atom to the excited state, absorbing a photon, and therefore a photon got destroyed. Whereas here, the excited state came to the ground state through sigma minus, and in the process a photon was emitted by the atom. In other words, a photon was created. So this is the Hamiltonian. It has these three parts. I will now proceed for the better part of this lecture discussing the Jaynes-Cummings model and the kind of dynamics that comes out of it. The detuning parameter, of course, is omega naught minus omega. Now let me work with delta equals 0. In other words, the frequency of the radiation field exactly matches the frequency omega naught here. Then the Jaynes-Cummings Hamiltonian clearly takes on this form. Sigma 3 plus h cross lambda, sigma plus a plus sigma minus a dagger. Before we look at the dynamics and what happens to the system when it evolves with this Hamiltonian, let's try to find out what are the various commuting operators in this problem. What are the operators that commute with the Hamiltonian? Consider the operator n, which I define as E plus a dagger a. What is the commutator of n with the Hamiltonian? I will remove the hat. We will do well to remember that this is an operator. First of all, there is a term a dagger a here, which certainly commutes with itself. A dagger a commutes with sigma 3 because sigma 3 merely involves the atom operators and not the photon operators. So essentially we need to find out, apart from constants, the commutator of a dagger a with this object. Now this is as far as a dagger a is concerned. What is the contribution to this commutator from this operator? Clearly this commutes with a dagger a because this is an operator pertaining to the atom and that to the field. I need to worry about the commutator of E with sigma 3, but E commutes with itself and not with GG. So basically it is the commutator of E with GG. This comes with an h cross lambda. This comes with an h cross omega by 2. And then of course there is the commutator of E with this object sigma plus a plus sigma minus a dagger. Let us work with a typical state. For simplicity we consider unentangled factored state n direct producted with G, which means that the radiation field is an n photon state and G is the ground state of the atom. So let me first look at this. This commutator is trivially 0 because it expands this way. And G and E are orthonormal kets and therefore this is 0. So I need not worry about this term. Essentially therefore I simply have to look at the commutator of n with this last term, the interaction term. So let us look at the commutator A dagger A with sigma plus A plus sigma minus A dagger, let us say acting on this ket. This is a direct product state of the atom and the field. Remember that sigma plus and A can commute with each other. Similarly, sigma minus and A dagger can commute with each other. So this acts on Ng. Sigma minus acting on G does not give a contribution. Therefore, I am left with this. Sigma plus acts on G to give me ket E. So I just have A dagger A squared ket N ket E from this term minus A dagger A sigma plus acting on ket G gives me ket E. But I also know that the commutator of A with A dagger is 1, and therefore this is the same as minus A dagger minus A dagger A ket N direct producted with ket E, which is minus A ket N direct producted with ket E. So this is this commutator which I have just now evaluated. This commutator is minus A ket N direct producted ket E, and of course A on ket N gives me a root N ket N minus 1, but for the moment I am just keeping it as such. I need to evaluate this commutator. What does that give me? Once more, I need to find out the action of this commutator on that state. This plus, I am expanding out the commutator. Acting on the state, the factored product state ket N ket G. Once more, sigma minus cannot contribute. Sigma plus takes ket E to ket G to ket E. So I have the first term is this A acting on N minus the second term is again A acting on N sigma plus Eg, but that is 0, note that the ordering is important. This object does not commute with this. Since that is 0 and there is a contribution here, this is A ket N direct producted with ket E. So I have evaluated this. And as you can see, the two cancel out. And therefore, I have shown that this operator N commutes with the Jaynes-Cummings Hamiltonian. I could have used any other combination of states, direct product states, any basis state in general, and I could have shown that this commutator is indeed 0. Of course, there is an expansion for the identity operator in this manner, because recall that there are only two states, it is a two-level atom effectively. This is not perturbation theory. The population transfer is primarily between two levels, and therefore I have this identity. I now define a Hamiltonian h cross omega n plus h cross omega by 2 identity, and another Hamiltonian which is minus h cross omega identity plus h cross lambda sigma plus a plus sigma minus a dagger, the familiar interaction term of the Jaynes-Cummings Hamiltonian. If you now look at H1 and H2, they commute with each other. N commutes with the identity. We've just now shown that N commutes with this part, the interaction part of the Jaynes-Cummings Hamiltonian. It's clear that the identity operator commutes with everything. Further, what is H1 plus H2? When I expand N in terms of the field operators and the atom operators, and the identity operator in terms of the atom operators, I simply get the following. This simply becomes the original Jaynes-Cummings Hamiltonian. Here is your h cross omega a dagger A. I need to have, and this part is already there. And now between these, it is clear that I have h cross omega by 2 ket bra E, that's one operator. And I have a minus h cross omega by 2 ket G bra G, thus giving me sigma 3. So indeed I can write this Hamiltonian, the Jaynes-Cummings Hamiltonian, as H1 plus H2, where I have set the detuning parameter to be 0. And now I work with this Hamiltonian and try to see what kind of dynamics comes out of this. Let me start with the state, the factored state, factored product state, or the disentangled state, n direct product G. That means it's an n photon state. Initially, this is my initial state, and the atom is in the ground state. What are the various states that are possible here? Of course, the ground state could become the excited state. But this could have happened only if a photon was absorbed, and therefore n went to n minus 1. So what is an arbitrary state of this system, which means at any time t, what is the state? Perhaps I can write this as Cg of t e to the minus I h t by h cross. Let me call this psi 1 and this as psi 2. These are basis states. I use E because psi 2 has the atom in the excited state, and I use G here because psi 1 has the atom in the ground state. Recall that these are not functions of time, they are basis states. This is the manner in which the basis states evolve, and in general I have some superposition coefficients. But let us now look at e to the minus IHT by h cross, say on psi 1. This has two parts which commute with each other, e to the minus I h2 t by h cross, e to the minus I h1 t by h cross. They commute with each other, acting on the state psi 1. But what would this give me? If I look at e to the minus I h1 t by h cross psi 1, this has two parts. H1 itself is here, it has an n and it has an identity. So, n has A dagger A plus EE, and then it has the identity operator. Of course, this comes with the coefficient which I have not put down, it's omega there, and then e to the minus I omega t psi 1. Now, this is simply a phase. Now, if you look here, this commutes with this. I can always write this as e to the minus I omega t A dagger A, e to the minus I omega t E E, acting on psi 1. If you look at psi 1, that has a g in it, and if I expand it, it is only the leading term that will contribute, because E and G are orthogonal states. So, there is no contribution from here, and as to this, it simply picks up an n, leaving the original state as such. What we have therefore seen is that the effect of H1 is not to produce any interesting dynamics, but to merely give an overall phase. So, let us not worry about the action of H1 of t. This would therefore, as far as the dynamics is concerned, this would simply amount to looking at the effect of H2 of t on psi 1. Again, H2 of t, H2 times t, not H2 of t, H2 times t, has two parts. One is the identity, which is not going to change anything, it is merely going to produce an overall phase. So, the only non-trivial contribution comes from e to the minus I lambda t sigma plus A plus sigma minus A dagger psi 1. I will use the same argument to show that here also I need to only worry about what the interaction Hamiltonian does to psi 2, everything else becomes an overall phase. What would happen here? First of all, psi 1 has g, and therefore, sigma plus acts on g to make it e. I expand this exponential. The leading term is simply n direct producted with g, and then of course, there are effects because of the other terms in the exponential. Whatever it is, the only two states that can contribute are ket n direct producted ket g and ket e direct product ket n minus 1. And therefore, all this simply amounts to some combination here, which is a function of time. I will call that C1 of t ket psi 1 plus C2 of t ket psi 2. So, apart from overall phase, which we need not worry about as far as the dynamics is concerned, we need to only consider the interaction part of the Jaynes-Cummings Hamiltonian, and there too finally what I have can only be a superposition of these two states. This is something I could have told even earlier, because if only two basis states are allowed effectively in our problem, at any instant of time, psi of t must be a combination of those two basis states. So, even as we did in the semi-classical example, let us look at the Schrodinger equation. So, here again I need to worry only about H2 psi of t as far as the dynamics is concerned, and this gives me IH cross C1 dot of t psi 1 plus C2 dot of t psi 2, that is the left hand side of the equation, equals H2 C1 of t psi 1 plus C2 of t psi 2. This is the Schrodinger equation. So, let us see how this simplifies. The right hand side, let me write that again, the left hand side is C1 dot of t psi 1 plus C2 dot of t psi 2 apart from an IH cross. H2 essentially has H cross lambda sigma plus A plus sigma minus A dagger. So, if you look at this, what would I have? I will have C1 of t H cross lambda sigma plus A plus sigma minus A dagger acting on psi 1 plus C2 of t H cross lambda sigma plus A plus sigma minus A dagger acting on psi 2. Notice that psi 1 is n cross g and psi 2 is n minus 1 direct producted with E. By cross I meant the direct product. So, this is just H cross lambda C1 of t, sigma plus g gives me E and A on n gives me root n ket n minus 1. This of course does not act and give you anything substantial, plus H cross lambda C2 of t, sigma minus gives me g and I have an A dagger which gives me root n ket n. So, essentially I have H cross lambda C1 of t root n psi 2 plus H cross lambda C2 of t root n psi 1. Of course, I can cancel the H cross on both sides of the equation. Put the I here on the right hand side and this is what I have. So, here we have the equations. C1 dot of t is lambda by I root n C2 of t and C2 dot of t is lambda by I root n C1 of t. Of course, these are coupled equations. We can differentiate them once more and decouple the equations. That gives me trivially C1 double dot of t is minus lambda squared n C1 of t. What is the solution? Well, the general solution would be A cos root n lambda t plus, well, I can write the general solution as e to the I lambda root n t. But you see the initial condition will now play a role. Let us choose the initial condition that initially the population was all in the ground state. That means the initial state was G direct producted n and therefore C1 of 0 is 1 and C2 of 0 is 0. That clearly tells me that C1 of t will only have the component coming from the cosine, it is cos root n lambda t, and C2 of t is minus I sine root n lambda t. This is very much like the model that we studied yesterday, the Rabi model. Of course, there is a frequency here which is given in terms of root n lambda, but then otherwise there is merely a population transfer from one state to another state, and we can see that the probability of being in the initial state is cos squared root n lambda t and the probability of going to the other state is sine squared root n lambda t. No difference from the semi-classical counterpart. But on the other hand, if I had started with an initial state which was in the excited state, say E n, and then the atom could have come to the ground state. So, E would have become G and n would have become n plus 1. Now, if I repeat the calculation, everything will go through, and it is a simple matter for you to check out that root n would be replaced by root of n plus 1. You would have the following. So, you would have a situation where root n is replaced by root of n plus 1, and that would have come about because when sigma plus acts on G, its counterpart is A, and A acting on ket n plus 1 is root n plus 1 ket n. Similarly, when sigma minus acts on E, its counterpart is A dagger acting on ket n, and A dagger on ket n is root n plus 1 ket n plus 1. What does that mean for this solution? It means that if I had started with an initial state ket E ket n direct product, this is my initial state, in this case ket E ket n. Everything will go through except that here I will have n replaced by n plus 1. Now, in the Rabi model, it is clear that since the radiation field was E naught cos omega t, if you switched off the field, there would be no transition from the excited state to the ground state. But now, look at what you see here. If there were no photons in the radiation field, suppose n were 0, even then you have C1 of t is cos lambda t and C2 of t is minus I sin lambda t. In other words, there is a non-zero probability of transfer of population from the initial state ket E of the atom to the final state ket G in the absence of the external field, in the absence of the radiation field. This is precisely what I remarked about in an earlier context when I discussed spontaneous emission. Spontaneous emission corresponds to a situation where there is no photon which is interacting, but the atom in the excited state could randomly give out photons and come down to the ground state. This is a purely quantum mechanical phenomenon with no classical counterpart, and that is what we see here also, quite unlike what we saw in the semi-classical model. So, the atom emits photons, absorbs photons, emits photons, absorbs photons. This keeps happening spontaneously, quite independent of whether there is an external radiation field interacting with the atom or not. So, the principle of spontaneous emission, that concept which I explained in one of my earlier lectures, you are merely seeing its signature out here in this case. So, there is another place where you see it, and that is the essential difference between a fully quantum mechanical model like the Jaynes-Cummings model and a semi-classical model like the Rabi model. Now, instead of looking at a situation like this, where the radiation field is in a photon number state, and therefore, there is merely a sinusoidal variation of the population transfer, and the only interesting phenomena that we can see is spontaneous emission essentially. You look at a situation where the initial state of the radiation field is the coherent state, for instance, some interesting superposition. Now, in that case, the matter is going to be very different, because an arbitrary state psi of t is going to involve a summation over n cos root of n plus 1 lambda t apart from alpha to the n by root n factorial and a whole lot of terms. Similarly, it would involve sine root of n plus 1 lambda t, apart from a whole lot of factors. First of all, of course, psi of t is an entangled state. You might start with a factored product state, but the dynamics entangles the state, and it rarely happens that the state comes back to its original factored product state. That is called a revival, and I will comment about it shortly. In general, it is an entangled state as time evolves, although initially it was an unentangled state. Further, the dynamics is very interesting. As I said, if you look at relevant quantities, they could come back to their original values at certain instants of time or over a certain period of time. In this example, if you look at the population atomic inversion factor as a function of time, which is the probability of being in the initial state at that time minus the probability of being in the final state at that time, this shows a very interesting aspect, which is a non-classical effect called collapses and revivals. What are collapses and revivals? Over a certain period of time, there is quiescence, or the inversion factor stays put at a given value, and then there are revivals. That means rapid oscillations, again a quiescent state, and then there are revivals, rapid oscillations, and so on. So the system collapses to a quiescent state, revives, collapses, revives, so on and so forth. These collapses and revivals are seen in the Jaynes-Cummings model with no classical counterpart. In general, a revival could happen under very many conditions. Essentially, the return of a system to itself would indicate a revival. It could even be the state of the system. For instance, the wave function for a system could come back to itself apart from an overall phase at certain specific instants of time, periodically coming back to itself, so that it comes back apart from an overall phase to its original value at instants separated by a basic revival time called T revival. In general, this does not happen. This happens because of the dynamics, because of certain nonlinear interactions, because coefficients, relevant coefficients are tailored just so, and so on. Without looking at the details, I merely want to point out to you the kind of rich dynamical structure that quantum physics can show. In units of the basic time of revival, T ref, you can sometimes see that the system comes back to itself apart from an arbitrary phase, and therefore this is 1. Certainly, therefore, all expectation values come back to themselves, and you would say that the system has revived. I want to show collapses and revivals for a different model. The model is the Kerr-Hamiltonian I have spoken about earlier. So this is an effective Hamiltonian, and the initial state that I consider is ket alpha, which is just the coherent state of light. So initially it is a Gaussian in position space. As it evolves through this Hamiltonian, the Gaussian no longer preserves its property and in fact changes very wildly, but it turns out, for details which I will not go into right now, through some very interesting periodic properties, at n times T ref, there are revivals. The wave function comes back to itself at these times apart from an overall phase, and therefore all expectation values come back to themselves. In this situation, we can calculate certain expectation values and see how exactly they behave. So let us look at these expectation values. As you know, the quadrature variable x is a plus a dagger by root 2. I have defined nu as mod alpha squared. Ket alpha was the coherent state, and alpha itself has a real and an imaginary part which I refer to as x naught and p naught, x naught by root 2 and p naught by root 2. Now if you compute x as a function of time, the expectation value of x as a function of time, remember that the initial state was a Gaussian, but as I indicated, the Gaussian loses its shape and form almost instantaneously as it moves through the Kerr medium, and the manner in which the observable varies in time is given by this expression. If you look at this expression, suppose nu were chosen large, the exponential term will dominate. It comes with a negative sign out here, and therefore x of t really does not change with time because there is an e to the minus large quantity here, except at those instants of time where t is pi by chi or n pi by chi. So let us look at just pi by chi. So t is pi by chi, and then you see this quantity becomes 0, and therefore all these objects start contributing, and therefore at the time t equals pi by chi, you find that x of t would show a change in its value, once more going back into a constant value, an almost constant value for other times. So only at this instant you would find that there is a large variation in x of t. Now if you computed x squared of t equivalently delta x, you could have computed p squared of t equivalently delta p of t and so on. The expression would be like this. Apart from some overall constants which add up, you have an e to the minus nu 1 minus cos 4 chi t times objects like this. As you can see, for nu large, x squared of t would essentially be this apart from a factor of 2, and therefore will not show any change in time. But then when t is pi by 2 chi, you find that once more this quantity disappears, and therefore there is contribution from here, and there is a sudden jump in a plot of x squared of t, expectation x squared of t versus t, similarly expectation p squared of t versus t, or even delta x versus delta p, because delta x the whole squared, as you will recall, is expectation x squared minus expectation x the whole squared. And that is what I will show in animation now. So the first plot is to see how exactly things vary at instants pi by 2 chi. Now, but before we go to the plot, before we go to the animation, I want to make the following statement. I have already said that at time pi by chi, x of t shows a sudden change because this becomes 0. What happens when t is pi by chi? X of t becomes its original value, there is a revival, and the Gaussian comes back to itself. If you look at x squared of t, at t equals pi by 2 chi there are sudden jumps. A phenomenon called fractional revivals occur. What is a fractional revival? Where the initial Gaussian splits into a superposition of two Gaussians. They are smaller in height, so they are in a sense copies of the original Gaussian, but not identical. You would call that a 2 subpacket fractional revival. At t is pi by 2 chi. Similarly, at t is pi by 3 chi and 2 pi by 3 chi, you will expect a 3 subpacket fractional revival and so on, because there will be 3 Gaussians and so on. So, it fractionally revives. It is a Gaussian form, but not quite a reproduction of the original, but you have 2 Gaussians here, 3 Gaussians here and so on superposed on each other. Revivals and fractional revivals are very interesting non-classical effects. There are no counterparts in classical physics. I am showing this just to give you a feel for the kind of rich dynamics that quantum evolution can produce. So, now let us see. Now, this is a plot of delta x versus delta p. As you could see, things did not move, it just stays still, except at the 2 subpacket fractional revival time when it moves. The same kind of thing can be seen if you look at x squared versus p squared. There is quiescence, except at that instant t is pi by 2 chi when you saw the red ball moving, and again there. Now, if you look at x cubed versus expectation p cubed, as I said, it should happen at 2 instants of time, the oscillations, and that is happening there. It moves and then there is quiescence. Did it twice and that is all. So, basically you find that for large nu there are these sudden jumps at certain instants of time, and you capture signatures of revivals and fractional revivals in observables. As you know, quantum mechanics largely is about the study of observables, outcomes of experiments, and these are interesting signatures of non-classical behavior which you capture in observables. With this, I have more or less concluded formally my set of lectures on introductory quantum mechanics. To quickly recapitulate, these are the various topics that I handled. There were many modules. The first one was operator methods, operator algebras. We looked at the angular momentum algebra also here without reference to orbital angular momentum. But then we had linear vector space concepts, the Hilbert space, and applications. So, the applications were to 2 and 3 level atoms, angular momentum and so on. We examined the postulates of quantum mechanics, and then in this abstract language we studied the problem of the oscillator, the harmonic oscillator. I connected that up with quantum optics and to interesting superposed states of the radiation field like the squeeze state, the coherent state and so on. The next module was about functions of position and momentum. The wave function was introduced, psi of x, its Fourier transform psi tilde of p. Of course, this involved understanding one-dimensional potential well problems, redoing the simple harmonic oscillator problem in the language of the wave function, the hydrogen atom problem, the charged particle in a homogeneous magnetic field, and therefore what you mean by a gauge choice. The third module was what I call dynamics 1, where we looked at the Ehrenfest theorem, the time dependent Schrodinger equation, so evolution of stationary states and superpositions of states, and also the alternative picture, the Heisenberg picture. We interrupted the dynamics by going over to an approximation method, the stationary perturbation theory, where we looked at the non-degenerate case, and then of course the degenerate cases, linear Stark effect and the Zeeman effect. Came back to dynamics 2, where I emphasized atom optics and tried to give you a sketch of a semi-classical model of the radiation field interacting with the atom, and then a fully quantum mechanical model mentioning in passing about certain non-classical effects. You already know about squeezing. I have just mentioned things called revivals and fractional revivals. throughout the course, I have attempted to take aspects of quantum optics along with the understanding of introductory quantum mechanics. And I have tried to show you how quantum superposition plays a very big role in certain interesting states of quantum optics. I have interspersed my lectures working out certain problems like the quantum beam splitter and so on, and illustrations of the Baker-Campbell-Hausdorff formula. Wherever possible, I have used examples from nuclear and high energy physics, for instance the shell model to illustrate the importance of the spin orbit coupling, and charge independence of nuclear forces, the concept of isospin, so on and so forth, which is very followable at the level of introductory quantum mechanics and the tools that one use in introductory quantum mechanics. With this, I conclude my lectures. I would not be doing a complete job of this unless I thank the members of NPTEL who have supported me during this. My thanks are due to Professor Mangal Sundar, who is the coordinator of the NPTEL program, Mrs. Usha Nagarajan, who is the principal project officer, Mr. Kannan Krishnamurthy, who is the executive producer. And then coming to the video recording team itself, I have to thank Mr. Ravindranath for adjusting to various changes in my video scheduling, the excellent support given by Mr. Ramachandran, who is the project officer who led the video recording team, Ms. Vidya, Mr. Subhash, Mr. Sabapathy, Mr. Sridharan, and Ms. Pradeepa. It was very pleasant. People were very helpful, most accommodative and professional. Good people to work with. I thank you all.